Hi everyone, today we are going to be looking at pages 349 through 352. We're going to be looking at lesson 25-1. So arcs and central angles. Let's go ahead and take a look at our learning targets for today. So we're going to understand how to measure an arc of a circle, and we're going to use relationships among arcs and central angles to solve problems. So we're going to go ahead and look at a story problem before we look at specific geometry vocab to help us understand what this unit is about. So let's read below. It says, Chris plays soccer for his high school team. His coach wants Chris to improve his accuracy on his goal shots. So at practice, the coach stands centered between the goalposts, and he has Chris try to kick a goal from different positions on the field. He has noticed that Chris's shots go anywhere from right on target or 15 degrees on either side of his target, to the left and right. So with this information, the coach thinks he and Chris can find locations of the soccer field from which Chris can be sure of kicking between the goals. So it says your teacher is going to provide you with a diagram of the soccer field. We're going to put that in the margin on the right side. So we're going to see point X is where the coach plans to stand, and we're going to have A and B represent the goalposts. Go ahead and copy what I'm going to give you in the margin, either into Notability or in your textbook's margin. Keep in mind, this is going to help us visualize where Chris is going to be best on the field to get his soccer goal in the actual goalie pin. So go ahead in the margin over to the right side. I drew the soccer field diagram. So we have points A and B. They represent the goalposts. We have our coach standing here, and we're trying to find what is going to be a good spot to stand from. So go ahead and copy this down in your margin, or go ahead and draw this in Notability. Once you're ready, go ahead and continue playing the video. So because we are doing this through video, we're going to have this activity be a little bit different than when we were in the classroom. So if we're in the classroom, I would provide you with a diagram that kind of helps us figure out how we can work with our 30-degree angle, and it would also show the bisecting ray. To talk about our bisecting ray, let's look in the margin below. It says a bisecting ray is a ray whose endpoints is the vertex of the angle, and it divides the angle into two congruent angles. So really, it divides our angle exactly in half. It bisects it, and it's a ray. So that means it has one endpoint and an arrow on the other end. We can also see that it is being used in our story problem here. So what we're going to do, because it's going to be a little hard to do this activity without the visual, is I'm going to talk it through with you. So our goal is kind of to test these three different points right here, and we're going to see if using a 30-degree angle that we set up, if we're able to make it within the goalposts. So what it's asking us to do is, it says we're going to look at the points that Chris makes his kick. The bisecting ray is going to represent the path to the target. And we're picking a 30-degree angle because that just means there's 15 degrees on each side. So that makes sense. So his kick will represent the bisecting ray, and then we have 15 degrees on each side for the air. So we're going to use this kind of angle visual as a tool to help estimate the outer boundaries of Chris's kicks when he aims at point X from different parts on the soccer field. So number one says the 3 points, as we have labeled on the soccer field diagram, are going to be the different positions that he's on the field to attempt his shot. We're going to actually start off looking at point 1. So when we set up and have our vertex at point 1, and we draw our 30-degree angle, it's actually going to look a little like this. So let's start off with point 1. What's going to happen is it's going to actually perfectly, let's try that again. It's going to perfectly line up just like this. That's actually what's going to happen. Now, could I draw it a little bit straighter? Yeah, let's try that again. Let's see what happens. Okay, so I'm going to try now doing this, trying it a little bit straighter. So I have Perfect, lined up there. And I'm going to have it lined up here. So what will happen is we are going to have these perfectly lined up like so. So you can go ahead and draw this as well. I know I'm a little bit off on the one that lines up with B, but it's going to line up exactly, and we kind of have this bisector going through it. Perfect. So that's what's going to happen when we look at point 1 and we have our 30-degree angle. So question number 1 asks, will Chris's shot be guaranteed to end up between the goalposts from point 1? So what do you think? Do you think a shot will be guaranteed? Yeah, I think it is, because we can see that each side of the angle contains a goalpost. So let's go ahead and write that down. So we are going to say for number 1, yes, because each side of the angle contains a goalpost. Now, we're going to continue and have this same visual, but we're going to use it on our next page to answer questions number 2 and 3. So let's go ahead and head to the next page. So I'm on the next page, and I set up the same visual over here for us to look at. Now for number 2, we're going to go ahead and start placing kind of that 30-degree angle. We're going to try it on point 2. And then we're also going to show it on point 3 and see if those places are going to allow for Chris to make his goal. So what I realized is when I put my player Chris on point 2, what happens is we have our 30-degree angle looking like this. So what happens is it's actually in between the goalposts. So before, in number 1, in point number 1, it was exactly on the goalpost. This is now between our goalposts. So it asks us, okay, is Chris's shot going to be guaranteed to end up between the goalposts from point 2? Yes, we can see for point 2 that it will. The sides of the angle, they're inside the goalpost. So I'm going to say yes for point 2, since the sides of the angle are between the goalposts. So you're probably starting to notice a pattern. You're probably going to figure out what happens with point 3. So let's go ahead and test it out. Again, if we had our measurement tool, this would be a lot nicer. I'm kind of just eyeballing it for you guys, using 30 degrees every single time. So for point 3, what happens is when we draw our lines for a 30-degree angle, you can see that we're kind of back a little further. So that way it's going to be a smaller angle here and kind of open up. We can see that bisector kind of goes through it right there. Again, I know these are sketches, but these bisectors should be aiming right at where our coach is at point X. All right. So we can see from point 3 that, can we guarantee for Chris to make the shot? Well, no, there's a little bit of margin of error. We can see the sides of this angle, they're outside the goalpost, so some shots will go wide. So let's go ahead and answer that. So we're going to say no for point 3, since the sides of the angle are outside the goalposts. And our hint is really that some shots will go wide. All right, so that's question number 2. Moving on to question number 3, it says, with continued experimentation. Now, I know this is a little bit hard to visualize and see. We're going to try to do our best. but we should find that there's actually a region of this playing field that we're looking at, okay? There's a region where Chris is guaranteed he's certain to have a shot in the goal zone, despite that, margin of error of 15 degrees. We're going to try to look at the soccer field diagram, and we're going to try to test out points on the field to see if we can make an informed conjecture, meaning making a math guess to the shape of this region. And then we're going to write a description of this region to see what it looks like. So we can see it recommends at least 8 points. I mean, we're going to kind of eyeball it and try to look at it together. So we'll try to get a higher number close to that. So as you can see, what I'm doing and what I'll have you do is I'm testing out kind of different points that will actually guarantee Chris to make the shot. Now, kind of helping you out, I mean, I could test points from outside here, I could test points in here, but what we're going to realize is all the points kind of inside this curve area. So I could pick any points all in there will guarantee that Chris will make the shot. And I know it's kind of like a do your best curve, but I kind of looked at it in relation to finding, a point that's over here that works, kind of on the reflective side, and a point that's over here that works. It's going to make this nice little curve. So we're going to see any points outside of this. We cannot guarantee that Chris will actually make it. So we're going to see all right here, and I could keep continuing this on, like even right here. We can see that it kind of makes part of a circle, right? This includes point 1. It includes, point 2 inside of it, right? And the goalpost, and this is actually called an arc. Cool. So that's what we're going to go ahead and write down for number 3. So we're going to say that we're looking at parts of a circle or part of the circle. And it's going to include, that includes, ready, point 1. Point 1 is going to be on that. And it includes the goalposts. So this is called an arc, A-R-C. Again, it also includes point 2 as well. We can include that in there. We just know it doesn't include point 3. Sweet. So the whole beginning part of this lesson was introducing this idea of an arc. So now what we can do is we can kind of zoom down below and start looking at some of our vocabulary words. So let's go ahead and look in the margin. We're going to start off with a central angle. So that's an angle whose vertex is at the center of a circle and whose sides contain the radii of a circle. So we can see that if we look at our picture for number 4, that if we look at AOB, it creates this angle, and we're going to see that this piece inside here is our central angle. It has the radii as the sides. Now it says an arc intercepted by a central angle. So this arc right here, that's actually called our minor arc. Oop, let me pull out my highlighter. That's our minor arc, so I'm going to highlight it right there. It lies on the interior of the angle, and the reason it's called the minor arc is usually because it's less than half of our circle. It's less than 180 degrees. So that's what we're looking at here. All right, so here's the part of the class where you're going to go ahead and head to our calendar and pull out our additional vocab sheet. We're going to be continuing on with circles, so go ahead and pull that out, and we're going to add some of this vocabulary to it. All right, so here is our word wall that we have right here. I'm going to go ahead and add some of the definitions and pictures of what we're going to be looking at, and then we're going to add this along the way. So go ahead and pause the video and write down what I have here. All right, so we can see we have a central angle is an angle whose vertex is at the center. So we have our example angle BAC drawn here. All right, the next piece we can see is our minor arc. That's an arc that measures between 0 and 180 degrees. So we can see on our picture that that's going to be arc BC. Something else to keep in mind is that for minor arcs, we use 2 letters to label. So that might be a notation you want to put down. Something that we also learned is the measure of the minor arc is actually equal to the central angle. So that's something that we saw there. That measure of this angle right here is the same as the minor arc. All right, let's look at the major arc. So it's an arc that measures between 180 and 360 degrees. So I have that highlighted here. I also added another point because remember, we actually need 3 letters. So we're going to use 3 letters to label these. So we're going to call it arc BDC. We're going to stop here right now and we're going to jump back to the book and continue on with this in a little bit. We're going to jump back to page 351 and we're going to start looking at number 5. Number 5 says, given circle C, we have diameters JR and KQ. And we know the measure of angle RCQ is 50 degrees. All right, so it says use the definitions for a central angle and the intercepted arc along with triangle properties to find each of the following. So I went ahead and labeled the 50 degrees inside here. So let's go ahead and see if we can answer each of the questions. So it's asking us for the measure of arc RQ. So remember, that's going to be our minor arc. It's the same measure as our central angle, which is 50 degrees. So I'm going to go ahead and put in 50. We already have the degrees there. So now it's asking for what's the measure of JQ, this arc right here. So we know already that this is 50 degrees. Oh, I'm going to pick a different color. There we go. That's 50 degrees. And we know that this is our diameter. So think of how many degrees are in half a circle? Well, 180. So that means in order to get the length of arc JQ, I have to do 180 minus 50. So when I do that, I get 130. So the measure of that arc is 130 degrees. If we keep going, the next one we're looking for is angle CRQ. All right, so CRQ. Wait a minute. This brings a new idea kind of into play, right? Maybe I have to draw a little bit to add on to this. I essentially am looking for this angle measurement right there, right? I kind of drew a straight line connecting Q and R. How do I figure out this amount? Well, keep in mind, remember, both of these, CQ and CR, they're radii. So aren't they congruent to each other? Couldn't we put a congruence tick mark here and here? And wait a minute, let's look back at this. Isn't this an isosceles triangle? So doesn't it mean that these 2 bottom angles will be congruent to each other? It does. So we know the 50 degrees, whatever's left, so we do, 180 minus 50, that's 130 degrees, and we just divide it by 2. That's essentially what we're doing. So we're taking the 180 degrees, we're subtracting 50, and we're dividing it by 2 to find one of those angles. So when we do that, we actually get 65 degrees. So this idea of triangles is actually coming back into play. Whoa, freaky. So let's look at our next one, the measure of JQR. So JQR, wait a minute, that's kind of asking us to take that minor arc of 50 degrees and this other minor arc of 130 degrees, and it's asking us to kind of add them together. It's really asking us for what's the measure of the arc which our diameter goes through. And we always know that's going to be 180 degrees. Looking at now the measure of JKQ, so we have JKQ. So we're essentially looking for this piece added to this piece, added to that piece. If we're looking at our picture, we kind of see we have vertical angles on both sides of C. So I know this is 50 degrees. So what does that mean? I know that this arc will be a measure of 50 degrees as well. Kind of looking at the process of elimination, this angle right here and this angle right here are also vertical angles. So this measure of 130 degrees is the same on this side. So I can label that 130 degrees. And now we can see we add the 50, 130, and the 50 together. So I'm going to do the 50. Ooh, let's pick a different color. I'm going to pick the 50. We're going to add the 50, and then we're going to add the 130 together. So lo and behold, when we do that, we should get a result of 230 degrees. So that's what I'm going to fill in as kind of the measure of all three of those arcs put together. I know it kind of looks a little weird to look at, but it's good to see. All right, looking good so far. Okay, let's keep it rolling. We're on the last one. Oh, this is one where we don't even have to find a measure. We're trying to write a congruent statement. So it says arc JK is congruent to which other arc? So which arc do you think it's congruent to in this picture? That's right. We could say arc RQ or QR, that arc, whatever it is, we want to make sure to put that symbol above it. So look at that. We applied our new vocabulary and we're able to figure out what we need to do. Looking pretty cool. So let's look at number 6. It says, write a definition for congruent arcs. So we're really going to see congruent arcs are arcs that have the same measure, right? So let's fill that in. So we're going to say congruent arcs are arcs that have the same measure. Let's keep going and scroll on down to number 7. It's a little bit of a bigger one, so we might need to zoom out for that. Oh yeah, got a couple other problems down there. There we go. All right, so it says given circle C with diameters JR, KQ, now we added PL, and another important piece of information is that we know PL is perpendicular to JR. So we know that this creates a 90-degree angle. And we know that KQ, it actually bisects angle PCR. So we can see angles 1 and 2 will actually be congruent to each other. So it's asking us in part A to explain why arc PQ is congruent to QR. So I'm going to go ahead and highlight those. Why is arc PQ congruent to PR? So go ahead, take a second, think about that. Well, keep in mind, we know that KQ, it bisects angle PCR, right? So we know the measure of angle 1 and angle 2 are congruent to each other. That's definition of angle bisector, right? So that means the measure of angle PQ is going to be equal to the measure of the measure of arc PQ is equal to the measure of arc QR. That's the definition of the measure of an arc. So all in all, that shows us that arc PQ will be congruent to QR. That's by definition of congruent arcs. So now we're going to go ahead and write this down together. So we can see that KQ bisects angle PCR, so we know the measure of angle 1 equals the measure of angle 2. And since we know angle 1 equals the measure of arc QR, and we know angle 2 equals the measure of arc PQ, that means the measure of arc QR equals the measure of arc PQ. So therefore, PQ is congruent to QR. And again, they are both arcs. Awesome. Let's go ahead and keep moving on. Let's move forward. So now it's asking us to add together the measures of angle 1 and angle 2. So remember, we know that JR and PL, they intersect each other at a 90-degree angle. So we know when we add angle 1 and 2, that is actually going to be 90 degrees. So remember, that's 90 degrees as well. All right, let's keep going. So part C says now let's look at the measure of arc JP. So we have this arc right here, JP, and it wants us to add it together with PQ. So looking at that all together, we want to see how we can fill it in and kind of add the part plus part equals whole. We can apply this idea to arcs just like we did with angles before in segment addition. So overall, we're looking for those two arcs added together to equal arc JQ. We're going to go ahead and kind of write down our sample explanation as well for this. All right, so I said similar to segment and angle addition postulates, we can add part plus part to equal, forgot the equal sign, to equal the whole with arcs. So we saw this last semester and we can apply it here. All right, Looking good so far. Let's keep going. Let's look at part D. So it wants us to find the measure of JQ, that arc. So we want to find JQ. So, we're probably going to have to find out what the measure, and I'll specifically add a color, what the measure of this angle is right here. So JCQ, because we know since it's a central angle, it'll have the same measure as the inscribed arc, that minor arc. So really, we know that angle 2, we know that's 45 degrees because it's half of 90. And we also know that angle JCP is already 90 degrees from that perpendicular interaction. So we know essentially we're adding 45 and 90 degrees. That's kind of our goal here. So altogether, we know for that arc, JQ, we're going to get 135 degrees. Now, I want you to go ahead and pause the video right here, and I want you to try to answer E, F, and G on your own. Go ahead and click play when you're ready to come back and go over these. All right, let's go ahead and go over this. So looking at part E, again, we have to kind of add in this triangle. We realize it's an isosceles triangle since we have radii as the sides. So what we want to do is we want to take 180 degrees, subtract the 45 degrees of angle 1, and divide it in half to find the measure of angle JRQ. That's going to be 67.5 degrees. Looking at the measure of arc JL, again, remember this is a central angle, so it will be the same measure as the arc. So that's 90 degrees. And then our last one, we also have to draw an isosceles triangle because we're trying to find, this angle measurement of JRL. So we have to take, our 180 degrees, subtract out the 90 and divide it by 2. That's exactly what I did here to find the angle measures here. So that's going to be 45 degrees. All right, so depending on who your teacher is, go ahead and check what your homework is going to be for the weekend. For Miss Graham's class, you don't have any homework for the weekend. So nice job keeping that in mind. But before I release you, we're actually going to go ahead and fill out the rest of our word wall. So go ahead and turn to back to your word wall. We're going to fill this in, and then you are good to go. All right, we are going to continue filling out our word wall here. So let's go ahead and start right where we last left off, looking at the measure of the major arc. So to find the measure of our major arc, which we have in red, it's actually going to be 360 degrees minus whatever we got as our central angle. Now, I'm going to do an example just to prove it to you. So let's say we know the measure of our central angle. Let's say we know that that's 80 degrees. So I'm going to label 80 degrees here. All right. That means we know the measure of our arc BC. So we could say the measure of arc BC is going to be 80. Let's try again. It's going to be 80 degrees. This means that if we go down and look at the measure of the major arc, right? Looking at that, we're going to take the measure of angle BDC, and we have to do 360 minus 80 degrees. So that's going to give us 280 degrees. So let's keep looking downward. So we can see we have a semicircle. Here we can see a semicircle is an arc whose endpoints lie on the diameter. So we can see from our picture, this is our semicircle. I mean, this is also an example because they lie on the diameter. We know that the measure of a semicircle is always 180 degrees. Always, always, always. Now, looking at the example here, we could list this as EFG and put the arc symbol over it. Keep in mind that we know that the measure of arc EFG will always be 180 degrees, and we like to use 3 letters as well. So that's why I kind of added that extra point in there. Now we're going to stop there for today. So go ahead, enjoy your time off with homework, and we will see you next time.